I'm going to go over number 4 from the practice test, which was a little tricky, and hopefully what I have to say will clear some things up. And then from the review, I am going to do, wrong page. I'm going to do numbers 16 through 20 in the review, and then the last proof. So hopefully that will all clear some stuff up for us and help you be prepared for the test. So number 4, we'll just start with 4A. So we're given a triangle, or basically a triangle that's been bisected, 12x 6 15. Okay, so I'm gonna set up, this is a bisector, right? So I'm setting up 2 ratios that are equal proportions. So what I'm gonna do here is I'm gonna say that this is related to this. So x is related to 6 and 12 is related to 15. So since x and 12 are in the same triangle, I am going to put x and 12 on top. So again, that's because they're in the same triangle. Since 6 and 15 are in the other triangle, I'm going to put them in the bottom. So since 6 is related to x, I'm going to put it underneath x. And since 15 is related to 12, I'm going to put it underneath 12. So I'm asked to solve for x. So what I'm going to do is x equals 12 over 15. And I'm multiplying both sides by 6 to get rid of it. So since I have this equal sign, what I do to one side, I have to do to the other. So that's going to cancel out, and I'm left with this over here. And then I'll let you guys just use your calculators for this, kind of speed up the process. We're left with x equals 4.8. And so let me do number 4b because it's a little tricky. 4b, and then I'll move on to the chapter review. So we have something like this. This line's parallel to this line. Connect this to actually make a triangle. And we are told 5, 7. We are told that this whole side, that's terrible, is 18, and this side here is x. So what I want to do first is I want to find, or first of all, let's look at this. Is it a side splitter or is it an angle bisector? We don't have any angles bisected, and this line is parallel to this line, and it crosses through 2 of the sides, so we're going to use side splitter. So what the side splitter does is it relates this line with this line and this line with this line. So it's a little different than the angle bisector. But it's still, we have one triangle here and then another triangle here. So we're going to match the triangles that we want together. So there's 2 ways to do it. We can either find this length here and use the corollary, I think it's the corollary, or we can find, or we can leave it like this and find the total length over here to find the corollary. So, or to find the proper ratio or proportion. So what we're going to do first is we're going to set it up where we just find the total length of the side. So the reason I set it up the way I am setting it up is, again, 12 is the total length over here, so I have to match it with 18. So this one's a little different than this one. You have to match it with 18, and 7 matches with x. So up here I was doing it from the same triangle, right? 12 and x are in the numerator. Down here we're doing by part. So x and 7 are the same part, so I'm putting it in the numerator. 12 and 18 are the same part, so I'm putting it in the denominator. So then I am going to multiply both sides by 18 like we did up here. So 18 times 18. So because it's an equal sign, what we do to one side, we have to do to the other. We're left with this. X equals, I'll just quickly do this on the calculator. Again, 7 divided by 12 times 18. It's 10.5. So that's how you do those problems. Let us move quickly to stuff from the chapter 10 review. I'm just gonna so we're looking at 16 through 20 right here, and we're using this triangle here. So write this down. Okay, so the first question is, what is the simplest form of MO and MN? So MO here and MN. So what we're going to do, we have numbers here. That's the key. We know that MO is 6, and we know that MN is going to be 6 plus 2, which is 8. Now we got to simplify this down. We can pull a 2 out of both of these, so we're left with 3 over 4. So that's how we do number 16. Number 17 is a little more tricky. I think these are fascinating. It's kind of like solving a puzzle. You have bits and pieces, and you gotta put it all together to find the answer, right? So we're gonna look back at this triangle, and we have to find LE and EM. Except down here we were told the lengths. Up here we're not told the lengths. What we are told is that this line here is parallel with this line here. And that's it, basically. So what we have to do is we have to find out the lengths, or we don't have to find out the lengths of this side. We can just use what we know to figure all this out. So, because these two lines are parallel, we know that this angle equals this angle equals this angle, and by the reflexive property, this angle equals itself. So these two triangles are similar. What's good about that is that we know that they will share the same ratios for all the corresponding sides. So the relationship that this line and this line have is going to be the same relationship that this line and this line have. So we're going to do LE is going to be basically 2, EM is going to be 6, which is just 1/3. So again, this line here is not 6. It is not length 6, and this line here is not length 2. But the ratio of this line and this line is going to be the same as this line and this line. So it's very important that this is not the same distance as this. We have to be clear about that. So this is 17. We did 16. Let's do 18. 18, we're going to do something kind of similar. So we're doing the relationship between this line and this line. And so we know that all the corresponding parts are going to have the same ratio. So the relationship from here to here is going to be the same as the relationship from here to here. And we found out that from here to here, or that relationship is 3/4. So we know EOLN is going to share that same ratio, 3/4. So 19 is where it gets a little tricky, but not really. If you read 10.7, we're dealing with the perimeter of the outer triangle. So this triangle and the perimeter of this triangle. And so our theorem from 10.7, or one of our theorems, states that the perimeter the ratio of the perimeter of two similar polygons is equal to the ratio of the corresponding sides. So I found out that the corresponding sides have the ratio of 3 to 4. So therefore, the perimeter is going to share that same ratio. So 19 is 3 over 4 as well. Gets tricky with 20. 20, we are dealing with the area of the two triangles. Notice that it's EMO, so the innermost one, in respect to the outermost one. So actually, this should be 4 over 3 in 19. That's because we got to do it in respect to, so we have the outermost one, or the bigger one, on the top, and the smaller perimeter on the bottom. 20 is the area of the smaller one over the area of the bigger one. And our theorem from our other theorem from 10.7 says the ratio of the area of two similar polygons is equal to the square of the ratio of the corresponding sides. So we know that the corresponding sides shared a 3 to 4 ratio, right? And so all we're going to do is square that. That's our answer. You can also write this as 9 over 16 because we can distribute the square to both terms. Okay, finally, we'll go over number 32, which is the proof from, or the second proof from the review. So EAR, and we are given that PA is the geometric mean between PE and PR. So PA, you guys remember the geometric mean, it means that, I'll just write it first. It means that this is the same as this up here when we're doing proportional ratios. We are also told that PA bisects angle EPR. So that's our given. Those are our givens. And we have to show that prove angle E, so that's this angle up here, is equal to angle PAR, which is this angle here. So the easiest way to go about this, if you think of angles and similar triangles, all the corresponding angles are going to be equal, right? So we're trying to prove this. We know that this is equal to here, and we're also given a ratio. So I'm given two sides, right? Two sides and an angle. So that should make me think of SAS, two sides with an angle in the middle. So we have to check to make sure that that is that the angle here is actually between the two sides. We need the angle to be between the two sides. So we can just start with PE over PA equals PA over PR. And that is definition of geometric mean. Mean of above here is the given. And so we're done after that, so we move on to the next given, which is PA bisects angle EPR, which is given. And from that, we know that this angle here is equal to this angle here. So angle EPA equals angle APR. And that is definition of bisecting ray. Okay, so if we look here, we have PE, this line, and PA, right? And then and PR. So I think oh, sorry. It's kind of confusing. But anyways, this line here is similar to this line here, and then this line here is similar to this line here. And so it's kind of like if we shifted this down, right? It'd kind of match up, not quite. And then this angle here is equal to each other. So we have side, angle, side, and then side, angle, side. So we have the side, angle, side theorem, so we can say triangle PEA is similar to triangle PAR. And this is SAS, similarity. Now I can say angle E equals angle PAR, because corresponding the angles equal in sim triangles. So that is how I do number 32. Oh, you guys couldn't see that. There you go. That's how you do number 32. Again, just take the given, get as far as you can with the given, then take the next given, get as far as you can with that given, then try and piece it all together to get something to get to where you want to be. So when you see that two angles are equal with similar triangles, think I need to prove the triangle is similar beforehand. If you're trying to show that sides are similar or proportional, you can use either the angle bisecting theorem or the side splitter theorem, or you can show that they're similar. It's usually one of these two. It's not usually that you have to show the similar sides. So hopefully this is helpful for any of you who are stuck on any of these three sections.